Welcome to Study Loop.
So once again, we have a new problem. This time it's a 2000. We're given a 2004 Prius, and there's a driver inside the Prius. The driver happens to have a mass of 150 pounds. So mass of driver inside of the Prius is 150 pounds. And then there are no passengers in the Prius. The mass of the Prius with the driver inside happens to be 3,071 pounds. So that's the information we're given. The Prius itself is initially at rest, so the initial velocity of the Prius is 0 meters per second at time t0. There's a force applied to it. It's a variable force, so the force is a parameter of time, and then in terms of visuals, there's a certain uh, behavior of the force. So this is the force itself, and this is the time related to the force. Right here we have a time of 1, and then somewhere right here we have a time of 2, and then somewhere right here we have a time of 3. So these are in seconds. This is time in seconds. Remember, the movement is towards the positive x direction, so it's a positive movement. The other thing that happens is the car goes all the way up until, so this is 4 seconds, and then we have 4.5. So pretty much from this point up until that point, that's a time of 1.5 seconds. And then from this point up until that point, that's another 1.5 seconds. And then from this point up until that point, that's another 1.5 seconds. So that's the scenario we're given. We have a Prius, and there's a variable force being applied to it. And so in part A, we want to find the between the time interval t equals to 0 and t equals to 4.5 seconds. This is 0 seconds. We want to find the impulse of the force, which is j, or you could call it j subscript x. It's the same thing. It just means the impulse. In part B, we want to find the speed at 4.5 seconds, or the velocity at 4.5 seconds. In part C, at t equals to 4.5 seconds, at t equals to 4.5 seconds, there's this force right here, which happens to be 3,500 newtons. The force at the top right here is 8,000 newtons. Okay, and then this force is 3,500 newtons. The force at this level is 7,500 newtons. So those are the forces we have. So at t equals to 4.5 seconds, the 3,500 Newton force is replaced by a braking force, which we call Bx, and it's negative 5,200 newtons. Okay, so the braking force is applied to the Prius. So think about, a Prius moving this way. Well, maybe you have the window somewhere like that. So the Prius is moving towards the right, and then you have a braking force of 5,200 newtons opposing it. This is the positive x direction, and so the negative x direction will be that way. That's why we have the force as negative. So there's a force being applied. How long does it take the time it takes for the car to stop. So part A, we're looking for the impulse. Part B, we're looking for the speed at 4.5 seconds. And then part C, we want to find out the time it takes for the car to stop, or the Prius to stop. In part D, we want to find the change in the work itself, or the change in work done by the force Bx. Remember, the Prius will do some work which is change in kinetic energy, but that will be opposed by this force, so it's going to be, kind of like a negative change in kinetic energy. A negative change in kinetic energy. And then the last part of the problem, which is part E, we want to find the distance that the car travels before it stops. Okay, the distance that the car travels before it stops. So you can think of it as, this distance right here. What's that distance? Maybe you could call it's a displacement, so we can call it S. So just to draw a distinction right there, this is part A. So we have 5 parts to this problem. Okay, we have 5 parts to this problem. And so the first part A, we'll do that in the next page. So part A, we want to find the impulse. Okay, the impulse of the force. Remember, between T0 and T4.5. So let's go back to the graph itself. We have the visuals. This is the force, variable force, and this is the time. Remember, in general impulse, Jx is defined as the force times the time, but in this case, we have different areas. So we're summing up each section, each of these sections. Let's call this A, B, and C. These ones represent the areas of these shapes, but also they represent the impulse. So you're summing up those areas. You're summing up those areas which are functions of time. So from area, you could say from time 0 up until 4.5 seconds. So then we'll say this point right here, the upper point is 7,500 newtons. That's this level. And the second level is 3,500 newtons. So the impulse, Jx, is area A plus area B plus area C. So area A is just a regular rectangle with a height of 7,500 newtons, times the time, which is 1.5 seconds. Remember, going back, you see that the time between these 2 points is given as 1.5 seconds, and that's the same for each one. The second part is a trapezoid, so we have 3,500 newtons plus, this distance right here. We have this height, which is 7,500 newtons. And then you want to multiply that by the time interval, which is 1.5 seconds. That's the second area. And then the last area is just another rectangle with a height of 3,500 newtons. 3,500 newtons. And a width of, or base of 1.5 seconds. So if you simplify this problem, you get that the impulse is 2.475 times 10 to the 4 newtons second. So the SI units for impulse is newtons times second, because you're dealing with a force and a time. The second part of the problem, as you can recall, was supposed to find the speed at t equals to 4.5 seconds. So we want to find the speed of the Prius at 4.5 seconds. We'll still go back to impulse, but this time we'll define impulse differently. So remember, if you have the impulse is either the force times the time, but also the impulse is the um, change in momentum, or you could say the final momentum minus the initial momentum. So we need to find the mass of this system. So the weight mg or m, we're going to use this mass of the Prius and the driver times the acceleration due to gravity. That's given us 3,071 pounds. Okay, 3,071 pounds. And so we have to change the pounds to newtons though. Okay, we have to eventually change the pounds to newtons. So this would be 4.448 newtons over 1 pound. So we have to change that such that the weight of the system in newtons is 3,071 times 4.448. That gives us 13,659.81 newtons. So that's what we're going to use to get the mass of the Prius and the driver. So 13,659.81. All of that divided by g, which is 9.8 meters per second squared, and that's giving us about 1,394 kilograms. That's the mass of the Prius. So we're going to go back to this formula right here, and if the impulse is the same as mv final minus v initial, going back, you see that the v initial is of the Prius is 0 meters per second. So this part is just going to be 0. If we simplify the problem, we get v final is the impulse over the mass. We already have the impulse, which is 2.74, or rather 2.475 times 10 to the 4 Newton seconds, and then you divide that by the mass, which is 1,394 kilograms. That helps us get the final velocity, which is approximately 17.75 meters per second. That's the final velocity at 4.5 seconds. That's part B of the problem. This was part A. This is part B of the problem. Now we're going to shift our attention to part C. So going back, we see that in part C, they say at 4.5 seconds, the 3,500 Newton force is replaced by a braking force of negative 5,200. So that's a negative impulse. That's a negative impulse. So we're saying the negative impulse is the braking force times the braking time. And the sole question is, how much time does it take to for the braking force to be applied? That's what you're looking for, or the braking time. So we're looking for the braking time. So T braking equals to negative jx, or the impulse, divided by the braking force. The impulse now has become negative, so negative 2.475 times 10 to the 4 Newton seconds. and then we divide that by the braking force, which is negative 5,200 newtons, and so we end up getting a braking time of approximately 4.76 seconds. That's part C. So that's the time it takes to, if you apply the force right here, it's going to take a while to stop. Okay, so it's going to take a while to stop. So the Prius is moving that way. There's a force of negative 5,200 newtons being applied. And then we see that it goes all the way up until it stops. So the time it takes is 4.76 newtons. Part D, the question was how much work is done in that process in stopping the car itself. So how much work must be done on the car by the braking force? So first of all, we're going to get the change in kinetic energy. Remember the work energy theorem. This is the next slide. We'll say, the using the work energy theorem, we know that work is change in kinetic energy. But since we have a braking force that's being applied on the Prius, it's going to be negative work. It's going to be negative work. So we have 1/2 mv final minus 1/2 mv initial. Remember, mv initial for the Prius is 0. This is also the Prius. As a subscript, we could call this the final velocity of the Prius. So we can change that a little bit. We want to change this a little bit. So, just for purposes of clarity and making sure that you have the labels for your variables are right. Okay, so going back on 5, we see that the change in work, the work itself, work done to stop the braking force, the work done by the braking force, it's going to be negative work. Okay, this is going to be negative work. So you end up getting okay, we got to change that. You end up getting negative 1/2. The mass itself is 1,394 kilograms. And then the velocity is 17.75 meters per second, but we have to square that because this is kinetic energy. And so one of the things you want to remember is this work is negative because it's in the opposite direction. The car is moving this way, but the force is that way. This is the force, and the work done by this force is going to be negative. So when we plug in those numbers and do the computations, we end up with actually, I have to backtrack on that a little bit. The car starts from rest, so we want to find we want to clarify on that question. So part D, actually, before we move on, part D is saying how much work must be done on the car by the braking force to stop the car. Okay, so you could put a negative if you wanted to. Okay, you could put a negative if you wanted to, but then you don't have to. Okay, if you have very good diagrams, but in this case, you could see that multiplying those numbers, we get negative. So this is the work done by the braking force. So work done by braking force becomes negative 2.2 times 10 to the 5 joules. So that's what we have in this problem. Okay, negative 2.2 times 10 to the 5 joules. That's the work done by the braking force. And then in the final part of the question, in the final part of the question, we get to see uh, we get to see that we want to find, just going back, we want to find the distance traveled before it stops. So again, we have this Prius and it's moving, and there's a force applied on it. The Prius is moving this way, or rather, there's a force applied on it like that, the braking force. It's negative, and so the Prius is going to move a specific distance. We can call that D. Okay, we can call that D. Um, and the work done by the braking force to stop the Prius is going to be the braking force times the distance. Okay, so to find the distance, we take the work done by the braking force over the braking force itself, which is Bx. In the previous slide, you get to see that the work done by the braking force was negative 2.2 times 10 to the 5 joules. That's what we have there. And then we have to divide that by the braking force, which is negative 5,200 newtons. Negative 5,200 newtons, and that ends up giving us the displacement or the distance that we wanted. So our distance or displacement before it stops, so from here to there, it's going to be 42.3 meters. 42.3 meters. So, we have a diagram, we have a very good graph that has different portions. In part A, we're supposed to find the impulse, so we use the area of the graph. In part B, we're supposed to find that's part A. Part B, we're supposed to find the final velocity. We use impulse with the regular formula Ft, and we have to get the mass of the Prius and the driver. So gx over m, and that gives us the final velocity at 17.75 meters per second. I think I want to make sure that this one is not confusing. That's 7.5. And then the other thing is we want to find the velocity before it stops. We use the impulse, but the impulse is negative because now you're driving, and the impulse is in the opposite direction. So that's why it's negative gx, and we use that. The braking force is also negative by itself. It's given us negative 5,200. We end up getting 4.76 seconds. And then we want to get the work done by the braking force. That's just the change in kinetic energy of the Prius, but it has to be negative because the braking force is opposing that change in initial change in kinetic energy, or just the total change in kinetic energy, which is the work. So we get negative 2.2 times 10 to the 5. And then the displacement or distance done by the braking force becomes 42.3 meters. Hope you enjoyed the problem. Feel free to ask any questions or send comments my way, and have a wonderful day. Okay, thanks. Bye.